So we're going to really focus in now on a special case of two-dimensional motion called projectile motion. And to simplify things, we're actually going to start with a projectile that's launched horizontally. So if we're looking at projectiles, you could launch a projectile at some angle, or you could launch a projectile horizontally. Okay, so let me just show you like a little illustration of this. So like, if this is a cliff, we could launch a projectile horizontally. So this would be a horizontal projectile, or anything that's not horizontal. You could throw something upward, you could throw it downward. Would be a projectile at an angle. Okay, and so this is the case we're going to focus on first, because it's a little bit simpler than the other cases that could come up. Alright, so the thing about this is that, well, it comes down to this. Just like before, the way that we really can understand this is by looking at the two dimensions of motion separately. So when a projectile moves through the air, it's going to fly through the air, it's going to have some horizontal component to its motion, and it's going to have a vertical component. Okay? And if we think about acceleration, well, the thing that causes it to fall downward is gravity. Okay? And gravity is acting in that y direction, causing that y component of the velocity to increase. But if we really kind of chart this out in a table, what you're going to find is this. Okay, so for y, we have, since it's launched horizontally, we can say that, well, the y velocity, so v initial for y, is equal to 0 meters per second. And again, this is because it's been launched horizontally. Okay, there's no up or down component there at the beginning. And it's accelerating downward. Okay, so that's 9.8 meters per second squared from gravity. And we'll say here that down is positive for the sake of simplicity. Okay, and then on the x side of things, we said this was launched at a speed of 30 meters per second. Okay, so we're going to say that Vx is equal to 30 meters per second. And this, when we put this here, this is the only thing we're going to put here. And the reason why is because if we were to put acceleration here, acceleration for x is going to be equal to 0. Okay, the reason why is because there's nothing accelerating it this way. Gravity, acceleration from gravity is downward. Okay, well, we can't take this, something that's in this vertical direction, and put it in the horizontal direction because they're independent of each other. So it turns out that things that are moving, things that are flying through the air, projectiles flying through the air, have, we're going to say there's 0 horizontal acceleration. Now, if you really want to be, like if we were going to be doing some really intense analysis of projectiles, we would probably need to account for air resistance, in which that would cause it to slow down a little bit. But for a lot of the cases we're looking at, we can assume that there's no horizontal acceleration. Okay? And so from here, if we want to fully analyze this situation, we can say that the displacement for y, the distance it's going to fall, is going to be 50 meters. It's going to go downward 50 meters. Okay? And to go with that, there's going to be some horizontal displacement that we don't know. And all this is going to happen in some amount of time. And then when it hits the ground for y, it's going to have some final velocity for y. Okay? So we have this stuff going on horizontally. We have this stuff going on vertically. They're independent of each other, but the thing that connects them is time. Okay? And so now I'm going to real quick show you kind of an animation using Desmos of the path of a projectile. And so we can really focus in on the fact that the horizontal component is constant. Okay? Okay, so here I've actually recreated that exact situation. Okay? And I'm going to zoom in a little bit. Oops. Okay, so we have a horizontal projectile launched with no initial velocity in the y direction. Okay? And launched going 30 meters per second in the horizontal direction. Okay, and so you can see here, moving at a constant speed this way, you can see that it accelerates downward. You have this y component getting faster and faster as it goes downward. Okay, and this is it. This is projectile motion. This is a horizontal projectile. We have constant horizontal velocity. We have accelerated motion in the y direction. Okay, this is technically free fall. Okay, you have something flying through the air only being affected by gravity. So a projectile is an example of an object in free fall. The only thing causing its velocity to change is that downward gravitational acceleration. For you to succeed in this chapter, one of the biggest things for you to remember is that for projectiles traveling, that horizontal component is going to be constant because nothing is causing it to accelerate. Okay. Okay, so back to this example, we can, there's a couple pieces of information we can find. We can find how long it takes to hit the ground, t. We can find out how far away from the cliff it lands. And we can find how fast it's moving up and down when it hits the ground. Okay, so we'll start by finding the amount of time it takes to hit the ground. So, in order to do that, should we be looking at, do you think to find the amount of time, what quantities could we use to find that? Do you think we could use these horizontal quantities, or do you think we should use these vertical quantities? I don't think we have enough information here yet, so we're going to have to stick with over here. We could use this equation, that delta y equals v naught t plus 1/2 at squared. Okay, and now this is where we see why horizontal projectiles are simpler to work with. Okay, v naught y is equal to 0, so this term right here disappears. We don't have to deal with this piece when we're doing the solving. So we just say that delta y equals 1/2 times 9.8 meters per second squared times t squared, and delta y going to be equal to 50 meters. Okay, and just for simplicity's sake, let's change 9.8 to 10. Okay, so this is going to be a 10 right here. Alright, and so when we're solving this, we have 50 equals 1/2 times 10 times t squared, or 50 meters equals 5 meters per second squared times t squared. We divide that over 10 seconds squared equals t squared, so that t would be equal to the square root of 10. That means that t would be equal to 3.16 seconds. Okay, we can take that here. We can use that to solve for how fast it's going to be moving when it hits the ground, and also how far away from the cliff it will hit. We'll start with this one right here. Vx equals delta x over t. Okay, we're going to put that 3.16 right there. We're going to put the 30 right there. Okay, we multiply them. Okay, and we're going to get that delta x is equal to, we're going to say about 93 meters. Okay, we'll say about 95 meters. So it's going to land 95 meters away from the cliff. Okay, I'll have you go ahead and find what the velocity for y is. Okay, so velocity for y should be about 31.6, or yeah, we'll say 31.6 meters per second. Alright, you would use that equation right there. So when it hits the ground, about 95 meters away from the base of the cliff, its velocity has a component this way of 30 meters per second. And we have a downward component here of 31.6 meters per second. Okay, we could find the magnitude of this velocity, so how fast it's going total, because it's not going 30 or 31.6. It's going a combination of those things. And then we could also find the direction. Okay, you might think of a scenario where it would be helpful to find the direction of the velocity of a projectile when it's about to hit the ground. But we'll go ahead and stop this one there. Okay, and we'll get a little bit deeper into analysis of projectiles in the next two videos.